So far we've been talking about conservation equations, conservation of mass and conservation of momentum. Maybe we'll explore, today we'll do some examples, but where this is going is that, I don't know what disciplines you are in, but this is a simulation from a company called Ingrain. One of my faculty colleagues of Rami Grader went to work for them. And the basic idea is that you can define the transmission characteristics of rocks, the permeability of rocks, by taking the drill cuttings that come up from a drill well, a drilled well, CAT scanning them to find out the geometry of the pore space. And so in this you can see that this is a fabricated one. These are individual grains you see in kind of grayish color. And then once you have that, you can run a model to simulate exactly what the passage of fluids would be across from one side to the other. And if you know what the passage of fluids is in this small part, so the chip might be something tiny, the size of a fingernail as it comes out, so it's very tiny. But if you can characterize how much pressure you have to apply on the upstream side to the downstream side to get a given volume through it, you could do some complicated things as have multiple fluids flowing through it. So you see some bubbles, which are really droplets, I guess, moving through it. You could actually characterize the transmission characteristics of oil and water and gas in the system, and use that in an upscaled model to represent the whole reservoir, where you're getting the parameters, the permeability of the system, merely by doing a numerical simulation, so like a numerical experiment. So this company was bought out by Halliburton, I think. So it's no longer a separate company, but that's what they do. An interesting idea. And so in many of the things that we're trying to do, so that's in a porous medium, and we'll find out if we get to it today that in a porous medium we can throw away the v squared over 2g term. Inertial effects of flow in porous media don't matter because the velocities are so small compared to the viscous losses of the fluid. So that's one way of looking at it. The other way is we could look at an open system, not the pore space between grains, and I guess it's the same thing really, but look at this room and squirting a hose within the room. And so this is just a model as well. So this is an all numerical model, and it's really taking the concepts that we talked about, is you have lots of little control volumes. Fluid mass goes into one side and out the other side, and you track two things. You track conservation of mass. Fluid in minus fluid out equals accumulation in that volume. And you track momentum of the system. So we use conservation of mass, conservation of momentum equations, week 6 and week 7, to be able to do that. Can I replay it? Yeah. And so it's more complicated than anything we'll look at in this class, but you get the general impression, at least, of what's going on. So, and of course, the kind of cool thing about that, I think, is that a lot of the special effects that you see in movies, like sometimes, like curtains blowing in the breeze or something like that, are often numerical models, which are then rendered by draping something over them to represent the air that's blowing. It's carrying the curtain with it, and you render it somehow to be able to make an interesting movie out of it. Did that finish already? Oh yeah. So you see the same things. So same idea. Again, a simulation of water going into a box. We're solving the same two sets of equations: conservation of mass, conservation of momentum. You don't see the mesh of basically a sugar cube grid of elements which is covering this, which allows you to do that. And I remember one of the videos that we've looked at in the past was a guy whose name I don't recall, but he's a faculty member at Stanford, professor at Stanford, and he has an Academy Award, so he has an Oscar. And the Oscar, of course, was for special effects, and by developing effective, efficient methods for modeling fluids to be able to represent these systems. And so you see, so it's quite complex. So these are just models that do exactly that. And so in a more sophisticated way, these models solve for those two behaviors: conservation of mass and conservation of momentum, and allow you to be able to represent this response. Quite incredible, really, right? Don't you think? So those have been around, these ideas have been around. Certainly, they needed digital computers to be able to solve them, so they've been around since the 1950s and getting increasingly more complex since then. So that's kind of where we are going with this, if you see. So that's the finishing of our playing around. All right, so we left last time. So we made the point that we're talking about, now we're talking about conservation of energy in terms of kinetic energy. And of course, you'll recognize that the expression that we had with enthalpy is really the first law of thermodynamics. So that's the linkage, if you like, the Venn diagram that links 301 and 303 together, thermodynamics and fluid mechanics. And the essence of that was that when we talked about conservation of mass, okay, so volume in, volume out, the difference between those equals accumulation. Either accumulation by getting a denser fluid, like in a tire, or accumulation by filling up a bucket, like in a bucket. Conservation of momentum was just the F equals ma in a more sophisticated way. But both of those, well, the second one of those in week 7 had no viscous losses. So what we're doing now with the energy equation is just the fact that we are admitting the fact that in real systems, we have viscous losses. And this is what we finished up with last time. We're making the point that when you run the water down from the top to the bottom, then the turbine output, this is the turbine output, the negative pump head is the turbine output. It's equal to a positive number, which is this, minus a loss. So you reduce in a frictionless system, an ideal system, the pump head would just be the elevation difference between these two locations, but there's a loss in the pipe that we have to account for as well. And so when you pump it up at nighttime to be able to use this as a battery, basically, then we have to reverse the way because it's always upstream to downstream. And then the amount of pump head that we have to apply. So positive pump head is energy into the system, pumping, and it's equal again to a positive value here, plus an extra amount of energy you have to apply to be able to elevate it. So the bottom line is that each way you lose by some amount. And so that's the analog between dragging my bag in a rudimentary way across the counter behind me. So that's kind of where we are with this. So you'll recall that we had two expressions. I didn't mean to do that. We made the point that we have this first equation and this second equation. We have to make sure that when we're dealing with them, we're working, they're just stream tubes, and so what we're working with is flow between upstream and downstream. I feel my specs falling off my face. This has to be the downstream. I always, by convention, do it 1 and 2, but we've done this before. So this would be upstream velocity, upstream pressure, upstream elevation, and potentially upstream enthalpy, and the same downstream. C2 and enthalpy. So enthalpy, I guess we've defined as, and you would know this, is equal to internal energy per unit mass plus pressure over density by definition. And actually this, if we write it out a slightly different way, this is the first law. Change in internal energy is equal to heat rate in plus mechanical energy rate in. And we have to be a sign convention, so heat in or work in is positive, work rate in is positive. So we have to deal with that. And for that reason, that's accommodated by doing this as, this would be in versus out. I don't know why the book uses it, well, very specifically here, these are the differences. This is the mass rate, and so this term, so these are the same expressions, it's just that this is written in terms of chemical energy that we've done because it's equivalent to the first law. And this is just Bernoulli as we had before. Again, upstream, we talked about having work in here as a pump head. We drew this diagram, I suppose, in terms of these components. V1 squared over 2G, pressure over unit weight, and elevation. It's horizontal, so you've had to look at your review equations for the test. So one of these questions, this kind of concept, there's a drawing on there that I think is useful for your conceptual understanding. So it's obviously on there for a reason. So make sure you understand these kinds of diagrams. And I guess the other thing is we talked about a hydraulic grade line, HGL. Oh, sorry, that's EGL, right? That's EGL. Energy grade line. And the hydraulic grade line would just be the pressures and the elevations. But this pump head idea, I guess we've drawn it slightly differently. Last time we drew it like this. This is a pump head, and this is a head loss. They might not be equal to each other, but we could draw it that way. The other way to think about it also is kind of the way I'm going to draw it, and that is that this would be a pump head, and then this would be a head loss, right? Because you're putting the pump energy in here. It's just easier to write. It's perhaps easier to write it across here, but this is, whoops. This is the other way to draw it. So you can draw it any way you prefer, like that. And so this equation here is upstream and downstream. And the only other components are the pump head, and we said this is positive if it's a pump, negative if it's a turbine, hence the last things we talked about in this, right? And head loss, you know, that is always negative because you always lose energy. All systems are dissipative, is the term that would be used. So these are the two terms that are used. So we've used this once. We'll tend not to use this so much because this isn't really a thermodynamics class, but a physical class on physical fluid mechanics. And the other thing is that we can define the pump head as we have it here. The way that I tend to use it most is that the power, unfortunate terminology because we use W for relative velocity, right? Power is equal to the mass flow rate, lowercase m in this case, multiplied by gravitational acceleration. So this is in watts, this is in kilograms per second, and this is meters per second squared. And this is in length, obviously, since we're adding apples to apples. We can define it in per unit mass just by dividing both sides through by the mass rate. And the other thing, which isn't so important, but we'll find out and we'll need it today, is that we can define head loss in terms of what's referred to as the Darcy-Weisbach. 2 S's? No, 1 S. Good German name, right? Well, Darcy's French. Weisbach is Weiss is white. Don't know what Bach is except for a composer's name. And so this is just the velocity head multiplied by a coefficient. And what we'll find when we deal with pipe flow is that the losses that are present in the system are usually proportional to this velocity head term. And so KL by definition, since this is in units of length and the units of V squared over 2G are units of length, then by definition this has to have units of nothing. It's dimensionless. So that's it. And so that's what we will start from today. So as I say, I just wanted to do some examples to follow on from where we were last time, just to show how we deal with problems. But really, all we're dealing with is if we want to accommodate losses within a system for a one-dimensional flow, then it's just Bernoulli plus these two extra terms. We just need to be able to accommodate those terms appropriately. All right? So let's go through some examples. That's all I'd planned today. So here's some examples. A pump transfers water from two reservoirs. Well, we'd like only to work in metric, but that doesn't change much in this particular case. There's a head difference between the lower reservoir and the upper reservoir. We're flowing from one to the other, so we can label them upstream and downstream, even though one is elevated above the other one. So we mean flowing from and to rather than an elevation difference by upstream and downstream. The head loss within the pipe is given by this Darcy-Weisbach equation. We have to be careful because the velocity is the flow within the pipe. It's got to be defined somewhere, typically defined as the flow in the pipe, because obviously the velocity in these reservoirs, if they're large reservoirs, then the velocities in each of these, V1 is equal to 0, and V2 is equal to 0, right? Just means those surfaces aren't changing very much because it's got a big volume. KL is a loss coefficient. I don't know what it is. The relation between total head rise across the pump and the flow rate through the pump is given by this equation here, by this figure. So you can visit that. And we have a loss coefficient, so we know what this term is that we have here. So to set up the expression, we know that the pump head is equal to what? If we look at this equation here, we can write this equation. This is pump head. This is flow rate. And flow rate is equal to velocity times the area. We know that from just definition of what a flow rate is. And the equation of this, we can guess it to be equal to 2 minus q times 100, right? When q is equal to 0, then this is equal to 200. When q is equal to 2, so if this is equal to 2, then 2 minus 2 is 0, and this is equal to 0, and it's linear in between them. So this is just the equation of the pump taken from this. So we know exactly what this is as a function of q. What else do we know? We can write Bernoulli from upstream to downstream. We know that the pressure, we could write this 0.1 here and here, and then use the pressures that are those places, but it's a bit more cumbersome to do that. It's easier to use places where we know that we can get rid of those terms. And so we know that here the pressure is atmospheric and that the velocity is equal to 0. And that's true for this as well. We could use absolute pressure, but it just makes it more difficult because we can't get rid of these as zeros. We know that these aren't equal to 0, but I guess this would be 0, and this would be 100 feet. So we know what these are. And we know that this is going to be equal to some coefficient times v squared over 2g. And so we know that this v is equal to q over a. So we can write this expression in terms of velocity or flow rate, and we can write this equation in terms of velocity or flow rate. So that's it. So if we throw away all those terms, we're only left with elevation, pump head, elevation, and head losses, which is this expression here. We know what the pump head is. We know what the head loss is. We know that we can relate velocity and flow rate together because velocity occurs in this term and flow rate occurs in this term, so we have to normalize those somehow. And so if we throw each of these components in for this, and I guess we'd know that this is equal to 100 feet together, then we can solve. It gets complicated and it ends up being a quadratic equation, but it ends up being more complicated than we need to do, more complicated than you ever see in a test, of course. And you come out with a single value. You'd either come out with a velocity or you'd come out with a flow rate as a function of that. And so that's the way to do it. A second one, again using Bernoulli. So if you're pumping gasoline from an upstream location to a downstream location, I guess these questions are making the point that upstream and downstream isn't really elevation, it's based on the flow coming from and going to. So gasoline flows through a pump, it flows at a given rate, a volumetric rate. It has a density which is 68% of that of water, that's what specific gravity is. Head loss is given by Darcy-Weibach again, the coefficient K sub L is 0.3. And we have a pump in here which is applying power, and that power is 20 times 10 to the 3 joules per second, or watts, right? Running out of space. So this is 20 kilowatts, 20 times 10 to the 3. So again, now we can't get rid of the pressures because it's asking what's the pressure difference between upstream and downstream. So that is really saying what's the difference P2 or P1 minus P2 or P2 minus P1. And so the question is this and this we want to know. We want to know the difference between them. So in other words, we don't need to know the two values, but we need to know the difference between them, which is one value. So these together are one value. We have a velocity. Do we have a velocity? No, we don't have a velocity. We know that Q is equal to 0.12 meters cubed a second. So velocity 1 is equal to Q over A1. Velocity 2 is equal to the same flow rate over A2. We have the sections in terms of diameters. So pi d squared upon 4 gives you the area for each of those. So we have an area, we have a flow rate, we have a flow rate, we have an area. So we have V1 and V2 defined. We have an elevation difference between Z1 and Z2. So Z1 would be, I suppose, 0, and Z2 would be 3 meters. If we take this as Z equals 0. We have a head loss which is equal to 0.3 V squared over 2G. Be careful that it's defined in terms of a particular. You've got two different velocities because you have two different pipe diameters, a small pipe diameter and a larger pipe diameter. This happens to be defined in terms of the smaller diameter, so this is 1, so you just have to be careful. It's always related to the diameter of the pipe somewhere in the system, and so you just have to be careful with that. And so we've pretty much defined every term. I would probably write this as H sub P, just because that's easier for me. And I always know that H sub P is equal to uppercase W over mass flow rate times G, which is equal to uppercase W over flow rate times density. Right? This is mass rate times G. Just think of it in those terms. So I would use for this term that equation here. And so what the answer is, so what do you do? Rearrange it to get P1 minus P2 on one side. So you take this P2 over to the left and you move everything else over to the right. So you end up with this. You multiply both sides through by the unit weight, which is rho g. So that would be this. I'm going to get rid of the g in a minute. Right, so that's all that's going on there. And so if you multiply both sides through by rho g, this is what you get. And then you can take this g out and cancel it with all these, which is what they've done. So you can see that. And you figure out what you know. We know this is 3 meters. We know g. We know the losses, etc. We know the velocities because we know the volumetric flow rates divided by the areas. So we have each one of these, which is what this is doing here, these two. So we have each of the velocities, and we know that the energy going into the system, so I guess this would normally be this term here, bless you, would be HP. We divided both sides through by unit weight, so this would be HP over rho g, which is equal to, this would be equal to W over mass flow rate. So let me write it as Q rho. Times rho g. Seems kind of strange in terms of units, but nonetheless, I think that's right. And so anyway, you just substitute these components in. We know what the loss is, defined it. So I would prefer, I would solve it this way. I would solve it in terms of these terms. I'd solve it in terms of P1 minus P2 over unit weight. And then I wouldn't have to work. Everything would be in lengths, and it would be much easier. We know this velocity head term. We'd know the elevations in lengths. We'd know this in terms of a length, and we'd know this in terms of a length as well. And then when all is said and done, I just multiply both sides through by the unit weight. So anyway, just a different way to do it. So you get the rough idea anyway, hopefully. So it's just a matter of defining all of your individual terms. Okay, so another one. Well, we've kind of done this already, but it's making the same case of how much power you can maximally get out of a system. Again, we did it slightly differently. The question we did had a big reservoir down at the bottom, which this was going into, so that upstream 0.1 and downstream 0.2 for us, the velocity v2 was equal to 0. But that's not necessarily the case, as if you look here, the whole thing is that this is squirting out of the downstream location at some velocity, which is 6 meters a second. So this has to be v2. v1 is still equal to 0. So you just have to judiciously choose your locations. This time upstream and downstream are above each other. This would be our relationship. What's the maximum possible power output? So this would be what is uppercase W. And so the easiest way to do that, I would calculate HP. And so I know that upstream the pressure is 0, downstream the pressure is 0 because it's atmospheric. This is a jet that's coming out. The pressure acting on the side of the jet has to be 0. And so since pressures at a point are always universally the same in all directions, this has to be pressure equal to 0. The velocity here is equal to, so this is 0, this is 0, this is 0, this is equal to 6 meters a second. The elevation Z2, this is equal to 50. This is equal to 0. And do we know what the head loss is in the system? Well, we know the head loss is finite, I guess. It has to be, it can be large, it can be 0 if it's inviscid and the viscosity is not important. And it can be bigger than 1, bigger than 0 rather. And so we can leave that in. And if we rearrange this, we end up getting rid of a whole bunch of terms. And you can see the terms that we're left with. We're only going to be left with an elevation term. We're going to be left with a pump term. We're going to be left with a head loss term. And we're going to be left with both an elevation term and a v squared term. So these are the two elevation terms. This is the v squared over 2g term. This is the loss that's still left in there. The loss is not a length here, it's a length multiplied by g in terms of units. And the amount, the net small w is equal to this term. And so we know that, what is it? I never use lowercase w, work per unit mass flow rate, but we know that this is, we can relate these two to each other, so I guess W uppercase would be equal to W lowercase over G times mass flow rate times G, right, just by taking these two terms here and rearranging it. That's all we're doing here. So just multiply top and bottom by mass flow rate times G. You get rid of this G and you get mass flow rate on the top. And so that's the conversion that needs here, because they're asking for the power, and power is uppercase W, and you just multiply both sides through by mass flow rate. That's all we do. And so that's equal to this. We know this is 50 meters? This is equal to 6 meters a second, all squared, over 2. And mass flow rate would be, you must have a cross-sectional area, right? So sectional 2 area, must have a D2 somewhere. I don't see a D2. But this mass flow rate is going to be velocity 2 times area 2, which is velocity 2, which is this, times pi d squared, 0.4. So whatever that is. I didn't see it elsewhere, but it's somewhere. Yeah, but I'm sure it's there. But I don't see, is there a number in the question? I didn't see it. 1 meter diameter. Yeah, 1 meter, so fine. That's it. So that's all we're trying to do. So that's kind of what we'll use. So to go back, all we're trying to do is account now for the fact that we have energy loss in the system. Primarily we'll use Bernoulli. It turns out to be a one-dimensional energy loss equation. It turns out to be Bernoulli with 2 extra terms added. One is a pressure head, one is a head loss. We have to be a bit careful about the sign conventions we apply to them, but apart from that, it really is come down to just defining the geometry. The geometry is always a stream tube or a stream line between upstream and downstream, and we can use the same things that we used with Bernoulli. If, for example, we don't have enough variables defined here, we can use conservation of mass, which is V1 A1 rho is equal to V2 A2 rho. Typically densities don't change, and it's just continuity. So if you end up with less terms, then you know how to solve it. So in other words, if you only have, if you have 6 terms and you need 8, then you can use this to be able to get, if one of the velocities is undefined, you can use this to link the 2 velocities together, etc. And the other term that's in here is the alpha term, which we said last time. And that really is just, if you look at flow within a pipe or a stream tube, we've always assumed that viscosity is 0 and that the distribution of flow as a result is equal to this. So if viscosity is 0, then alpha is equal to 1. If viscosity is real and finite, then the flow regime looks like this, because we know from Newton's law of viscosity, clever guy, this Newton, dvx dz, that if this is 0, the boundary condition is typically that it sticks to the no flow velocity at the edges because it sticks to it, and there's a parabolic distribution between it. And so this means that alpha is less than 1, between 1 and 0. And so this term just accounts for that, the fact that this is a distribution. Okay? I'm not sure that's particularly important for us. All right, so I've got to talk for a few more minutes. Any questions? We never have any time for questions. Yes?
Could you explain the head loss again with the different diameter pipes?
Head in one of these questions related to?
It's up a little bit.
This one?
Yeah, so like how would we, what would happen if it was in terms of...
Yeah. So all I'm saying is that this head loss is defined in terms of a particular diameter. And so this is the head loss across the system. And I suppose in reality, what we might do is, and we haven't got there yet, is that we could at some stage, this is just a question where it's convenient to be able to define the head loss in the particular way it's written. But for instance, what we could do in this equation is we could write P1, we could write Bernoulli, and the right-hand side would be equal to the same three terms rather. And we could write two head losses. And so it could be the head loss in pipe 1, which is V1 squared over 2G. And we could have a head loss in the second term, which would be V2 squared over 2G. So they've defined, just to define the loss between section 1 and section 2 in terms of a single value, just as an expedience. But you'll see when we talk about pipe networks that this head loss term on the right-hand side is really a sum of head losses. And the head losses will actually ultimately define as head losses which are minor and head losses which are major, if you can see my handwriting. So interesting enough, the minor losses are the losses that occur in bends. So we'll see that you can get the value of this KL for a whole different bunch of bends. And just, why not? Let's take a leisurely look because we don't usually do this. I don't mean to give you epilepsy by having a look at this, but there's a very specific table I'm looking for. And so what we'll see is that when we look at fittings, such as valves and bends, then you can define a table that defines exactly this. So the head loss term that we've talked about is defined in terms of the velocity, always the velocity within the fitting, and depending on the severity of the fitting, the value of this goes up. So a flanged bend through 90 degrees has a head loss which is smaller than one which is threaded, because you might have threads on the inside that make the flow less smooth. And so you'd expect that this loss here is larger, and depends on the radius of curvature, the angle, whether it's 90 degrees or 45 degrees, and so we can get all these values. So typically when we talk about using Bernoulli, as I mentioned, we can talk about the sum of the head loss terms, which would be just equal to head loss 1 plus head loss 2 plus head loss 3. So if you had a piping system that had a bend in it, a bend in it, a bend in it, a valve of some kind that's not closed all the time, then there'd be a head loss here, there'd be a head loss here, etc. Well, actually a head loss rather than just K. etc. Nothing more than that. So in the question, they're just choosing a single value. So I guess the only point I was trying to make is that you have to be careful to choose the right velocity that applies to that particular head loss. That's all. Yeah. See if I can find back where I was. Good luck. Oh, that's the easiest way. God, that's a lot of writing in there, sorry. A lot of pearls of wisdom. I know you don't believe it, but all right. So, what else? Any else? Okay. Well, you know, of course, that doesn't mean we leave any earlier. So you can either question. You got to get your money's worth. So, what else? Yeah. Maybe talk a little bit about this. So, look around for hands up, no hands up. So we've made the case when we looked at those movies at the beginning of water squirting around, etc., that there's a differential analysis that's involved in here. And I don't know that I really want to talk in great deal about, I don't want to do more equations today. So let's just talk about how this might work. So I looked online before. I'm not sure what's going to come out of here. This is something that groundwater flow simulation at mine closure timescale. So this is kind of interesting. And so if you look at this, this is a plan view, as you could imagine. These are streams on the surface of this plan view. This is a lake, which these streams go into. And this is superimposed on the background of this kind of lattice grid. And so this lattice grid is really just the idea that each one of these little cells is a cell where we could write our Reynolds transport theorem. It happens to be dx by dy by dz, but that doesn't matter. And each one of these cells, what we can do is we can look at taking the cell, looking at the mass flow rate in, the mass flow rate out, and the imbalance between those would be an accumulation. And if we look at each individual cell, but write a system of equations that links it to all the neighboring cells, we'd end up with a system of equations where basically if we have 100 elements in this direction, 100 elements in this direction, so 10 to the 4 elements, then we'd have 10 to the 4, 10,000 equations which we need to solve that relate the flows into and out of adjacent cells to each other. That's all it is. And so relatively sophisticated numerical models are put together that allow you to solve this system, where these individual cells, they happen to be, I don't need the background here of how to do it. Each of these individual boxes is the little control volume that flow is going into, flow is coming out of, and the difference between those would be a net accumulation. And so if you write an equation for each one of these boxes and then solve them all together, you can get the flow distribution throughout this system. And that's really what the rationale of you having fluid mechanics is in this class, is that this is a mine closure problem. So that's a mining example. But certainly in mining, if you look at airflow, if you want to keep miners breathing, you need to look at ventilation in mines. So ventilation in mines is no different from an airflow problem within a pipe, just at a bigger scale if you're underground. If you're a petroleum engineer, then you're looking at getting fluids out of the subsurface. The same kind of equations apply as we've talked about here, and we'll define them next time. If you're an environmental systems engineer, then perhaps you'll be looking at this kind of mine closure problem. And if you're looking at energy engineering, if the equations for flow in geothermal reservoirs, for instance, are exactly the same as those in petroleum reservoirs and in groundwater aquifers. And so there's a commonality in here that we'll talk about. And really all it comes down to is using conservation of mass. So mass flow rate in equals mass flow rate out, and the difference between those represents an accumulation. And you end up with an expression that is only written in terms of mass, and what you need to account for is this second thing that we've talked about in terms of head losses. So we've talked about frictional systems here, and so clearly if you're squeezing fluid in very small pores, within a material. And we'll go back to this for those who didn't see it. So if you're squeezing fluid through the pores within this material, I guess I can let it run, then the drag on these little tubes, each one of these little tubes is just going through here. It's kind of an effective tube, right? It's changing in diameter as you go downstream. But each one of these tubes is exerting some drag on it due to friction. And this drag between upstream and downstream means that if you look at the pressure on this side of the cube and you look at the pressure on this side of the cube, they'd be different. And they'd be different by an amount which is pretty straightforwardly. I said I was not going to use any more equations, but of course I lied. The idea is this. And actually we had this equation written the other day. It's not a very good square. But we can do a force balance where we have a velocity 1 and a velocity 2. And we have a pressure 1 and a pressure 2. Pressure would be acting in this direction, right, as we know. Something's happening. Oh yeah. That's my DC meeting, but I guess we finished everything yesterday, so I'm not going to DC today. So we could very simply write an expression that is P2 minus P1 times A, which is equal to the sum of the shear stresses times the areas. So the shear stresses times the areas would be on these little tubes that come through. This would be a shear stress that's applied on this wall, tau. The area would be equal to pi 2 pi r, pi d upon 4, I guess, right? That's the circumferential area times the length. And we might have a whole bunch of these. So this is equal to tau A. This is tau. And so this is really the exposition. So we'd use mass balance to say mass in equals mass out, and the difference between those is accumulation. And then we'd have to constrain it to account for this fact that we have viscosity here that affects this in some way. So we need some way of being able to calculate the shear stress, and if we do that, we could calculate some function that retards the flow across it. And you might have seen it in your other courses. We call it permeability. And that is that the average flow velocity across the system is equal to a pressure gradient. This length would be L. This pressure gradient would be an upstream pressure, P1 minus P2 equals dP. And so what it's doing is it's linking an upstream, the loss of pressure across the system in driving the flow rate, and Q would be equal to velocity times area, this total area here. And so we define a term that defines that. So this term is called permeability. If you're a petroleum engineer, this term is viscosity, dynamic viscosity. And this is in units of length squared, meters squared, so in Darcy's, but that doesn't matter for now. And so this allows us, so this in a fake way, so I'd said before that when we talk about flow in the subsurface, we look at mass rate in equals mass rate out plus accumulation. Of course, there's no momentum balance in that equation. And so that's okay, we can do that calculation, but what we'd find is that we have too many unknowns in that system that don't say anything about the pressure and the velocity as it varies across the system. So what we need is another set of equations, which is kind of a fake way of representing the momentum equation. And this is kind of a fake way of representing conservation momentum. We're just saying that the resistance to flow is going to be equal to an equivalent drag, which varies as a function of pressure. And it's given by Darcy's law. This is, we already said Darcy-Weibach formula. After Henri Darcy, from the town of Dijon, who was manager of the fountains. You don't need to know the story now. But it basically says that the velocity of flow is proportional to the pressure gradient, the pressure drop between upstream and downstream, and multiplied by a coefficient which represents the behavior of the material that it's flowing through. That's all. And so we use that to be able to solve these problems. So mine closure for environmental systems engineers, dragging gas out of gas shales for petroleum engineers, and getting fluids through geothermal reservoirs for geoenvironmental engineers. That's it. So I didn't do my equations at the end of that just for a change today. We could have done. Maybe we'll do them next time. So next time we'll talk perhaps about porous media flow and show how we can very, very simply actually solve the flow equations actually in a very graphic format. And the graphic format is that we can, just like we could look at the flow lines around an airfoil, we ended up with kind of a rectilinear web of flow lines around an airfoil. If we look at what the flow lines would look like in a porous medium flowing across a dam, we can exactly use this geometry to say what the flow volume rates are through it. It's quite a neat technique called flow nets. 1 minute to go. The least equations you've ever seen in this class. Anyway, so, okay. All right, any other questions? Did you have a minute? No, fine, great. Well, great seeing you. I should count you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. I think I got the guys at the back. So anyway, so 23. So that's it. That's all I have today. We'll finish on this topic on Friday with what we talked about. Next week is the test. Don't forget that the test review session is online, and so have a look at that. You know I'm not going to try to steer you wrong, so the things that you see on that are probably relevant to what's going to happen. So. And I'll reiterate my comments about the progression through tests is that they do get more formulaic and more predictable as you go through. So at least take some joy from that as a pep talk. Okay. Thanks very much. Enjoy your day.